Hello friends, welcome to another tutorial in network analysis. In today's tutorial, we'll talk about solving a network with dependent source using 5 different techniques. I've done a couple of videos where I have solved a network using 5 different techniques. I'll put a link to those videos in the description. You'll find those videos very helpful and interesting. But in this video, we'll talk about solving a network with a dependent source. And this is the network that we have in hand. And this is, by the way, 10 volts. And just by looking at this network, you'll see that we have two independent sources, a voltage source and a current source. And this is a dependent source because this is rhombus in shape, and because we have a plus minus sign in it, so we know that this is a voltage source and it depends upon some other voltage V1 of the network, so it is a voltage dependent voltage source. And this dependent voltage source depends upon this V1 voltage which is dropped across this 1 ohm resistor. Now before we proceed on to solve this network using all the 5 different techniques, please understand that this polarity of voltage is very important. You must not ignore or underestimate the importance of this polarity of voltage which is specified here on this 1 ohm resistor. I'll tell you in a bit where this importance will pop up. So let us solve this network using technique number 1, which is KVL, or we call it mesh analysis also. We know that in mesh analysis, we take up loop currents in clockwise direction in all the loops. So by inspection here, we see that we have a branch which has a current source in it. So by inspection, I1 minus I2 is equal to minus 2. So this is the first equation that we get. And because of this branch which has current source in it, we cannot make loop equations for these two individual loops. So we'll take up a super loop. So in super mesh, let's begin from this element. So this is 10 and going from negative to positive, so with a positive sign we have 10, then again going from negative to positive we have a voltage drop of V1, then again negative to positive a voltage drop of 4 V1, and because the direction of the current is this, so this will be plus, this will be minus, so we're going from positive to negative, so a minus sign 5 I2. So you should be thorough with writing the loop equations in mesh analysis, and this is in turn equivalent to 0. Now this part is super important, where I mentioned that this polarity is going to play a vital role, because the direction of the loop current is assumed to be clockwise in nature and the voltage drop which is given is in the opposite direction. So I can say that by inspection this voltage drop V1 is equivalent to minus of I1 into 1, which is the resistance, of course, because voltage is current into resistance. So but this current is minus I1 because we need to calculate the voltage with a positive sign on this side and a negative sign on this side. That can only happen if we take I1 to be negative. So this is the super important point in this network, and this point is going to come up again and again while solving this network using different techniques. So if we know that our voltage V1 is minus of I1, we can simply substitute it here. And substituting this condition that V1 is minus I1, we get this second equation. So this is equation number 1, this is equation number 2, and solving these two equations we get I2 to be equivalent to 2. And by the way, we need to find the current through the 5 ohm resistor I0. So I0 is the loop current I2. So if we find I2, we get I0, and I0 is 2 ampere using the first technique. So let's get to the second technique, which is KCL, or the nodal analysis. So I've taken up the network again with this node labeled as A. So at this node 2 ampere current is entering and I1 and I2 are leaving. The reason I've taken I1 to be moving out of this node is that because we have a plus and a minus sign on this resistor already given, and this is by convention I've taken because I need to calculate I0. So the direction of I0 is also taken to be outwards from this node A. However, at node A, I1 plus I2 becomes equivalent to 2. Now comes the most important part. So VA, because the current is leaving from this node, so I'll take up VA minus 10 upon resistance 1 is the current in this branch. So VA minus 10 upon 1 is I1, and VA plus 4V1 upon 5 is the current in this branch I2, and this is equivalent to 2. Now comes another important part. If we know I1, we can calculate V1, because I1 into 1 will be V1. So that is how I've calculated V1, which is I1. I1 is VA minus 10 upon 1 into 1. So VA minus 10 becomes V1. So if V1 is VA minus 10, this dependent voltage source is also dependent upon V1. So this becomes 4 into VA minus 10, and I can substitute it here. All right. And that is what I've done. So I've substituted this thing in star, and I've calculated the voltage here. That comes out to be 10, and I1 becomes 0 because I1 is VA minus 10 upon 1. So 10 minus 10 upon 1 is 0, and we know that I2 is 2 minus I1 from this KCL equation. So I get the answer 2 amperes again. So this was also pretty straightforward and easy. Let's jump to the technique number 3, which is superposition theorem. As I mentioned in the previous tutorial, in superposition theorem we need to take one source at a time, but we do not eliminate dependent sources. So we have two sources here, two independent sources. We'll take them up individually in two different networks, but we will not eliminate this dependent source. So we need to calculate the current I1 because of 10 volt voltage source, and then we need to calculate current again, let us say I1 double dash because of this 2 ampere, and then we'll add them up. So when we take only 10 volt voltage source, we have 10 plus V1 plus 4V1 minus 5 I1. So I've taken up this loop current I1. So that turns out to be equivalent to 0. And so 5 I1 is equal to 5 V1 plus 10. But we know that V1 is simply minus of I1 into 1. So you can simply say that the voltage drop across this 1 ohm resistor is minus I1 into 1. Again, the direction of the current is taken to be negative because the voltage drop was given in such a way that it is falling in the opposite direction to that of the current. So V1 is minus I1 into 1, and substituting V1 is equal to minus I1, we get I1 to be equivalent to 1. So the current passing through this 5 ohm resistor because of 10 volt is 1 ampere. Now let's see how much current is flowing because of this 2 ampere current source. That is again very easy because we have taken up this node 1. At node 1, 2 is entering and this is leaving, this current is leaving, which is V1 upon 1. V1 is the voltage at this node, and again this I2 is leaving, which is V1 plus 4 V1 upon 5. Voltage drops upon resistance, so I get V1 to be equivalent to 1 volt. And because I need to find I2, so I2 is V1 plus 4 V1, because V1 is 1, so I get 5 upon 5, which is equivalent to 1 ampere. And again, superposition theorem says that the total current flowing through this 5 ohm resistor is the algebraic sum, because they are flowing in the same direction, so they'll be added up. So I get the answer 2 ampere, again using the third technique, which is superposition theorem. Now let's get to the technique number 4 and 5, which is Norton and Thevenin's theorem. Now if you have seen my previous video, I've mentioned that dependent sources can be solved very easily using Norton or Thevenin's theorem. It's just that we cannot find RTH directly. So the steps are to find VOC and ISC and then find RTH, which becomes equivalent to VOC upon ISC. So if any of the case that we take up, whether it's a Norton or a Thevenin case, we need to find out VOC and ISC. And once we find VOC and ISC, to find RTH, we can draw equivalent circuits for both the Norton and the Thevenin's circuits. So if you need more clarity on this, you can watch that video. I'll put the first step is to find VOC, and VOC is found by eliminating this load. So I have opened this load, so this open circuit voltage, this link is not there, so this is an open circuit voltage. And on this outer loop we see that 10 plus V1 plus 4 V1 is equal to VOC. And if we inspect this circuit more closely, we see that this 2 ampere current can only pass through this network portion. It can never go to this part because it's an open path here. So 2 ampere when flows through this 1 ohm resistor will drop a voltage of 2 volts. So very cleverly I've found V1 to be equivalent to 2 volt when the load is open. And when V1 is 2 volt, I can simply put it in star to find VOC to be equivalent to 20 volts. In the next step, we'll find ISC. And for ISC, I've shorted this load. You've seen that this 5 ohm resistor is taken out, and I've shorted the terminals of the 5 ohm resistor, and the current through that shorted path will be known as ISC. That is what we strive to find out, and we can find that out using mesh analysis again by inspecting I1 minus I2 is minus 2, and in this super mesh 10 plus V1 plus 4 V1 is equal to 0. And again voltage here is minus I1, so I can simply put minus I1 minus 4 I1 is equal to 0. I1 is 2, and putting it in this equation I get I2 to be equivalent to 4 ampere, and I2 is nothing but ISC. So my ISC is 4 ampere, my VOC is 20, so I can easily calculate RTH now. RTH is VOC upon ISC. It turns out to be 5 ohms. I can easily draw equivalent circuits. The equivalent circuit, Thevenin's equivalent circuit, will require me to use VOC and RTH in series with the load resistance, and my Norton's equivalent circuit will require ISC in parallel with RTH, which is also known as R internal or Rn. It's one and the same thing, in parallel to the current source and the load. So simply substituting the values here, VOC is 20, RTH is 5, load is 5, I2 becomes 2 ampere, which is the current that we've been getting so far using all the techniques. And my current source is 4, internal resistance is 5, load resistance is 5, so this 4 will equally get divided into these two similar resistances, so I get 2 ampere current at the load using Norton's theorem also. So all the 5 techniques, they've given me the same result, and that is how we can compare which technique is more efficient, which technique less time consuming, so as to be more proficient in competitive examinations. And I hope this tutorial on comparison of all the 5 techniques was of help. And if you liked the content of this video, please click that like button and consider subscribing to this channel and press that bell icon for all the notifications related to this channel. And thank you so much for stopping by and watching this video. I really appreciate it, and you have a good day and a great life ahead. Bye.